This video is on solving optimization problems for functions of a single variable. So the general thing that makes these things work is you have a function that you want to optimize, which means maximize or minimize. So, you're going to have some function initially of two variables, and this is going to have some, expression. And the thing that you want to maximize or minimize is called the objective function. And you're usually given some, or you're always given some equation in x and y, like some expression in xy equals some other expression in x and y, and then you use this, which is called the constraint equation, to solve for one of the variables and thereby eliminate one of the variables. After that, the objective function becomes a function of a single variable, let's say x, and then we just use calculus to find if you want maximum, then we find the maximum. If you want minimum, then we find the minimum. Okay, so let's do it. This one on the first page here turns out to be one of the harder ones, so I don't want to do that one first. Let's go down to this one, dorm room poster question. So the top and bottom margins of a poster are 6 centimeters and the side margins are 4 centimeters. The area of the printed material on the poster is is a certain number of centimeters squared. Find the dimensions of the poster with the smallest area. So you know what they're talking about, right? Like if we just look at some kind of poster. I don't particularly like Led Zeppelin, but they do have posters, and so we could look at, this isn't really helpful, is it? I'm just wasting your time. But here's a good example, right? So there's there are margins on top and there's margins on the side, and then there's a central area that actually has printed material on it. And so with the constraint here is that the printed material needs to be a certain number of square centimeters, and the margins need to have certain lengths. All right, so let's set it up. So first let's write the objective function. Actually, let's draw a picture. And you should draw a picture when you do this, or I will cry when I grade the exam. So trying to do this without a picture is impossible, or at least unnecessarily painful. So let's say that this is the outer part of the poster, and now let's try to draw what the inner part is going to look like. So we've got a little green strip there and green strip there, and like that. Gosh. Okay, so my picture is pathetic. Let me see if I can move it over. So that's slightly better. All right, and so what? We're supposed to have 6-inch margins on top. So that means this is supposed to be 6, and we're supposed to have 6-inch margins on the bottom too. So this is supposed to be 6, and we've got 4-inch margins on the side. So 4 and 4. So now let's label some things like the sides of the poster. So let's call this side Y because it's vertical and this side X. So one nice thing about the whole objective function constraint equation thing is it really lets you think less, because now I can just dumbly say the thing that I want to optimize is the area of the poster, which is X times Y. Okay, so I can just do that. And then I worry later about the constraint equation. So now I'm going to worry about this constraint. So what is this constraint saying? It's saying that the area of the printed material on the poster is 384 centimeters squared. So I need to express this, and so you might want to think for a second before I write it about what I'm going to do. But can you see that it's going to be x minus 12 times y minus 8 is equal to 384, that magic number. So see why? Because this length is going to be that, and this length is going to be that, and so their product is going to be 384. So now we're going to do just what we said, which is use the constraint equation to eliminate a variable. So let me solve for y here. So y minus 8 is equal to 384 divided by x minus 12. So x minus 12. So y is equal to 384 over x minus 12 plus 8. All right, and so let me save that. I'm going to need some space because I've got something else planned for later. So I'll just put that up there, and I'm going to erase this so I can kind of reclaim the space. All right. So now that I've eliminated a variable, the objective function becomes a function just of x. So what function is that? Well, x hangs around, but now I can replace y with this stuff that it's equal to. So I can just cut and paste this down here. 384 over x minus 12 plus 8. All right, and I guess I should multiply that in. Yeah, I'm just dreading doing this algebra. Yeah, but I don't see any way to get around it, so let's just do it. So this is 384 x over x minus 12 plus 8x. Now is the part where we just use calculus to find the maximum of this. So let me make some room for myself. Got kind of a room problem, don't I? Let's move this up here. And so I need to take the derivative. So what is a prime? A prime is equal to quotient rule time. 384 times x minus 12 minus 384x times 1 divided by x minus 12 squared plus 8 equals 0. Okay, so that's what I have to solve. Alright, so I need to put these things over a common denominator. I'm just going to push my little problem down here. So I'll put these two over a common denominator. So what's that going to look like? I'll have, I'm also at the same time going to multiply this in so I can collect common terms. So that'll give me 384x minus, let's just leave this for the time being as 12 times 384 minus 384x. So that's nice, you get a little cancellation. Plus 8 times x minus 12 squared. And now all this is over x minus 12 squared. Alright, so what did I do? I just put these two over a common denominator, which is x minus 12. And we've got, bam, bam! And now we've just got this on top. We've just got, so the equation that we really need to solve, you know, the denominator doesn't make any difference. So what we really need to solve is 8 times x minus 12 squared equals, sorry, it's premature equals, minus 12 times 384 equals 0. And so I've got x minus 12 squared equals 12 times 384 over 8. You can do this algebra at your leisure and just make sure that we're getting the same things. So that means x minus 12 is equal to plus or minus. Do I have to worry about the negative possibility? Probably not, but let's just leave it there for the time being. Plus or minus the square root of 12 times 384 over 8 plus 12. Okay, and I bet you that if we actually figure out what this term is, the square root and all that stuff, let's do it over here. That's the square root of 12 times 384 over 8, and what is that? Oh, I think maybe Sage logged me out, so let's use Google. after this. Oh shoot, there it went. It was 24. Still gonna work? Crap. Oh well. So anyway, we learned that it was 24 before it disappeared. So this is plus or minus 24. Let's write it as 12 plus or minus 24. Now I say that I don't need to worry about the possibility that it's negative, because x is going to be a... Oh man, I'm just making a mess, aren't I? Let me just clarify things here. I just did algebra like a student and added 12 over here, but forgot to take it off over here. Did you see that? That was really terrible. So we have this. So x is... Let me just kill myself and get resurrected and come back and start over. Alright, so this is what we've derived, but we don't need to worry about the negative possibility because x has to be a positive amount because this is a geometry question. So what we really have is x equals 12 plus 24 is 36. Okay, and if x is equal to 36, then it should be pretty easy to figure out what y is because of this relationship. So what's got to be true is 36 minus 12 is 24 times y minus 8 is equal to 384. And so y is equal to 384 over 24 plus 8. And please, Internet, tell us what that is. 384 divided by 24 plus 8. 24, so y is also 24. No, wait, x was not 24, right? But so the solution is that x is 36. Remember, x is 36 down here. X is 36, and y is 24, and that is the solution. So x equals 36, y equals 24. And that makes the area smallest, okay? So let's just check that it is a minimum. So we can do that by considering the second derivative. Oh Jesus. Yeah, I'm not going to do the second derivative, but you could in principle look at the second derivative of the area and make sure that it is positive at x equals 36, which means that this is the local minimum. Excellent. Gosh, so I've totally, I think have I lost that guy? Can I still recover him? Is he still down there somewhere? Come back. Oh, there he is. So I think this one is the second easiest one. So I'm going to do this question now. So you thought that I didn't explain that first one very well because I made my characteristic algebraic mistakes. Then this is a chance to get in on the ground floor. This one says that the manager of a 100-unit apartment complex knows from experience that all units will be occupied if the rent is $800 per month. Not in New York City, right? This question needs to be updated. Actually, I guess they would all be occupied at $800 a month, but the landlord, that's definitely not the optimal price. A market survey suggests that on average, one additional unit will remain vacant for each $10 increase in rent. What rent should the manager charge to maximize revenue? All right, so the thing that you want to maximize is revenue. So the objective function is going to be the revenue function. And revenue is going to be a function of n, which is the number of people in the building. So the number of peeps. And also the cost. So I'm going to say this is the monthly rent. So the amount of money that the landlord makes every month is just the number of inhabitants of the building times the amount that each of them have to pay. All right, no problem. So that's revenue, and this is the objective function. And now let's think about what the constraint equation should be. So this constraint equation is relatively complicated here. It says that one additional unit will remain vacant for each $10 increase in rent. That means that the number of people that live in the building depends on the rent. And what is it? So let's say that let's just imagine that the building is full, and then he says that one person is going to move out every time the rent increases $10 from $800. So take monthly rent P minus 800 and divide by 10. So I wish that I could somehow, use telekinetic or telepathic powers to make you see what I see. I just know from experience teaching this question that some people are going to find that incomprehensible, but look what's happening here. So the rent is going to be a little bit more than 800, right? Because it's going to go up some. And so then this is the difference between the rent and 800. And it says for each $10 increase, so by dividing by 10, you get the number of $10 increases. And then 100 is the number of people living in the building, and so 1 moves out every time P goes up from 800 by $10. That's what this is saying. So just like normal, we use the constraint equation to rewrite the revenue function as a function of a single variable. So let's do that. Actually, n is already conveniently solved for. So this is going to make revenue a function just of P. It's going to be 100 times, let's call this P over 10 plus 80. I just did a little algebra there, times P. And what is this? This becomes 180 minus P over 10 times P. And I'm just going to go ahead and multiply in that P too. So this is 180P minus P squared over 10, and let's take the derivative. So this is a stage where we're just using calculus to find the optima. So this is 180 minus P over 5 is equal to 0. Alright, so that means P is equal to 5 times 180, so do the algebra on your own and confirm. And this is $900. Okay, so that means that the optimal rent is $900. We should really make sure that this is a maximum, which means the function is concave up there. In this case, the second derivative is pretty easy to find. The second derivative is actually just minus 1/5, right? R prime prime is just minus 1/5. And so when the second derivative is negative, that means concave down, and critical point plus concave down means max. So this is the max, or this gives the maximum revenue. So this is the rent that maximizes revenue. Okay, great. So that answers that question. And let's go all the way back up to the top and do this one that kind of scared us at first. Get rid of this stuff. Find the dimensions of the largest rectangle that can be inscribed in a circle of radius r. Okay, so let's draw a circle. Help me, computer. If you get it close, it'll actually recognize it as a circle. Oh, yeah, it's brilliant. Okay, and so there's a circle, and we want the largest rectangle that can be inscribed in a circle. So largest means largest area. Okay, so this is starting to look a lot like the CUNY Graduate Center icon. So here we go, and let's label some things. So this is just general problem solving, and this is something that a lot of people in the exam will not do, and then the tears will start coming from my eyes. Because you have to, you have to draw a picture and label it. You have to start thinking. You can't, right? You've got to fight. And so let's write some things down. What is it we want to optimize? It's the area of the inscribed rectangle. So that's easy to write down. So the area of the inscribed rectangle is temporarily a function of two variables, x and y, and the area is just x times y. And now we need to use the constraint. So there are several ways we could do this. You could slap some axes on here and do it that way, and it would probably be a good exercise actually to do it that way. But I'm going to try to do it without axes. And the observation that's going to make that possible is realize here that the diagonal of this square always has to be the same as the diameter of the circle. Do you see? Like the little Ghostbusters strike has to always be just one diameter. You have to imagine it kind of turning. So as this thing turns, it looks like the rectangle is going to become more narrow like this, and if you turn it the other way, the rectangle will become more like that. But no matter what the rectangle looks like, the diagonal of the rectangle is always going to be the diameter of the circle. So I'm going to use that as my constraint, and that's just the Pythagorean theorem says that this is x squared plus y squared, square root. So what does that mean? That means the circle has radius r, so the constraint equation is going to be that x squared plus y squared is equal to 2r, because that's the diameter. So ready to go? How does it work? Use the constraint equation to eliminate a variable, then do calculus once you get the objective function as a function of one variable. So let's no, it's too early. So now we just solve for this, right? So x squared plus y squared equals 4r squared, and that means y squared is equal to 4r squared minus x squared, and that means y, you can forget about the negative possibility because this is geometry, and you've got 4r squared minus x squared. So that is how you eliminate the variable. Let me put it up here and get rid of this work. Okay, so now I'm going to use that expression for y to rewrite the objective function in terms of a single variable x. So now area as a function of x is x times the square root of 4 minus r squared minus x squared. And hold on to your hats, because there's going to be some brutal algebra here, and I'm actually kind of tired of making these videos, so maybe I'll go through it kind of fast. I don't know, but you should be able to do this. So it's going to be product rule, right? So take the derivative of x, and you get square root 4r squared minus x squared plus. Now leave x alone, and the 1/2 comes down, and the positive 1/2 becomes a negative 1/2, which puts the square root down here. And I know you might just be like, I hope you're not just agape at what I'm doing right now. Shouldn't that be that surprising? Given enough time, you should be able to do all these things, because, oh, where does that come from? From the chain rule. Okay, and again, the chain rule is the most important thing. You're not going to be able to do these problems if you don't know the chain rule. If you don't know where this came from, stop the video and open your book and read the section on the chain rule, because that's much more important, and you can't do these problems without knowing the chain rule anyway. Alright, so wait, this is a mistake. After my lecture on being a good student, I was a bad student. So see, where this comes from is it's the derivative of the inside. This is a constant, so its derivative is 0, but this has derivative minus 2x, which is where he comes from. So this is the derivative. We have to set the derivative equal to 0. So let's do it. Alright, so now I have just some things to copy over. Square root of 4r squared minus x squared plus, it's going to be minus x squared over the square root of 4r squared minus x squared equals 0, and we're supposed to solve this. So I'm going to multiply both sides by the square root of 4r squared minus x squared. And before I do that, I should make sure that it's not 0. And if it is 0, that is not a solution to the problem, because the thing that makes this stuff under the radical 0 is x equals 2r. In other words, x equals the diameter. And the only way x equals the diameter is when x is, here, which is obviously not a very area-rich rectangle, so it's definitely not the solution. So multiply both sides by this stuff, and then you get the radical goes away. You get 4r squared minus x squared because it just cancels there, equals 0. And this means that 4r squared is equal to 2x squared, and that means what? You've got 2r squared equals x squared, and so finally x is equal to the square root of 2 times r. Booyah! And then we're almost done. We should really find what y is. Y is going to be the same thing. Why is that? Well, one reason is that this problem just doesn't know the difference between x and y because it's a circle. But you can also show that it's true by plugging in x equals root 2r into this. What happens if you do that? You get y is equal to square root of 4r squared minus 2r squared. So that's the square root of 4r squared, which is, 2r squared. And that is the square root of 2 times r. So that's also what y is equal to. Right. So that's it. That's how you do the optimization problems.